Hello and welcome to Group 10 presentation of the article entitled Shielding Application from an Trusted Cloud with Haven, narrated and presented by Walid Al-Ahdal, Rich Sparks.
Part 1 Summary. Nowadays, cloud computing infrastructure are concerned with protecting privileged code of their platform from the user untrusted code. The cloud providers provide nothing to protect user data from access by their privileged code. Providers depend on a significant amount of trust from the cloud user. On the other hand, cloud users are required to trust that the cloud provider will not expose their privileged code and data that are hosted on the cloud, which may result in limiting cloud adoption. Any cloud user who wishes to deploy on the cloud must trust provider software, including privileged software such as hypervisor and firmware. They also must trust the entire stack of management software that the provider uses to maintain their platform. Cloud users must also have trusted provider staff, which includes system administrator as well as the staff with the physical access to hardware such as cleaning crew and security guards. Users must also accept that the fact they also rely on local enforcement and their policies of the jurisdiction where their data is stored and replicated. This is a huge trust commitment from any user, and it's currently a significant preventive to cloud adoption. The objective is to run an existing server application in the cloud with the level of trust and security roughly equivalent to a user operating their own hardware in a locked cage at a colocation facility. Also, the objective is to have the cloud provider only provide raw resources such as processor circuits, storage, and networking. The provider would have the ability to deny any service, but not observe or modify any user data except over the network. The cloud provider only control the resources, allocation, and protecting from malicious guests. The term for this type of operation is called shielded execution. So the goal becomes to provide the ability for shielding the execution when deploying on the cloud provider platform. Shielding execution protects the confidentiality and integrity of code and data from untrusted hosts. This guarantees to the cloud users the wanted secrecy when executing programs and storing data in the cloud. As a result, executing programs act as if they are being run on hardware under the user control. Haven Prototype is the product of the research teams from Microsoft and Intel that aims to solve the cloud computing's trust problem. Haven uses shield execution of unmodified legacy applications like SQL Server and Apache on a commodity operating system and a commodity hardware. Using shield execution protects the program and associated data from the platform on which they run, including the cloud provider's operating system, administrative software, firmware, and other software that support the application. To provide shielded execution, Haven uses two key features. One, Intel Software Guard Extension, or SGX for short, which is a set of new instructions that allow user-level code to allocate private region of memory. 2. Microsoft Drawbridge, which is a lightweight virtual machine for secure application sandboxing. As we previously defined, SGX is a set of new instructions and memory accesses that allow a process to initiate a secure region of memory address space known as an enclave, while cache-resident enclave data is protected by CPU access controls. SGX also allows CPU-based attestation, allowing a remote system to verify cryptographically that specific software has been loaded within an enclave and establish shared secrets, allowing it to bootstrap an end-to-end encrypted channel with the enclave. Besides protecting the content and integrity of memory mappings, SGX also mediates transition into and out of the enclave and protects the enclave's register file from operating system exception handlers. SGX also allow efficient multiplexing between multi-isolated programs.
Because isolation alone is not enough to protect applications, an isolation mechanism must permit interaction with untrusted software or hardware to communicate result or access system services. And it is at this point that a naive isolation program is vulnerable. Intel SGX shielded execution builds on an isolated mechanism to provide high-level security properties such as confidentiality and integrity. Confidentiality: the execution of the shield program appears as a black box to the rest of the system. Only its input and output, but no intermediate states, are observable. Integrity: the system cannot affect the behavior of the program, except by choosing not to execute it at all or a denial of a service attack. If the program completes its output in the same as correct execution on a reference program, Haven takes SGX to provide the needed security of shield execution to unmodified legacy applications. Drawbridge is described as a system supporting low overhead sandboxing of Windows applications. Drawbridge provides two core mechanisms: Pico process and library OS. Pico process is a secure isolation container constructed for hardware address space, but with no access to traditional OS services or system call. Instead, a narrow API of OS primitive is provided, implemented using a security monitor. Library OS is a version of Windows 8 refactored to run as a set of libraries within the Pico process, depending only on the API. Together, Pico process and Library OS enable sandboxing on unmodified applications with comparable security to virtual machine, but with much lower overhead. Together with Drawbridge, Haven enabling mutual distrust between host and guest. As we discussed, Haven influences Intel Software Guard extensions and Drawbridge to achieve shield execution of entire legacy application. Haven is designed to take into account two challenges: one, defending against a malicious host operating system, and two, executing existing binaries in an enclave. Defending against a malicious host operating system by limiting the scope of the host operating system by using libOS within the enclave. libOS implements the full operating system API but uses a tiny set of core operating system primitives. The libOS is under the user control and therefore can occasionally tested or inspected offline to ensure it is not malicious. Since the scope of attack reduced by libOS, careful defense coding exhausts the validation of untrusted input and encryption and integrity protection of any private data is needed to implement the libOS primitive in the presence of malicious host operating system. Haven takes advantage of Intel Software Guard extension to make a full application binary executable in Enclave. Intel Software Guard extension alone cannot guarantee the execution of a full binaries and Enclave due to the challenges of loading code and data at a runtime, dynamically allocating and changing protection on a virtual memory, executing arbitrary user mode instruction rising and handling exception, and using thread local storage. Haven addresses each of these challenges by using design enhancement to Intel Software Guard extension and modify libOS behavior. Shield module is to implement the drawbridge API required by the libOS. It includes private implementation of a typical kernel functionality such as a memory management, a file system, and thread synchronization. It also acts as a trusted bootloader for the libOS and application. The shield is responsible for protecting the libOS and application from logo attacks outside the enclave. This figure illustrates the architecture of Haven. An enclave is created within the drawbridge Pico process that contains the entire application and libOS. To protect the libOS and the application from malicious operating system, Haven uses two layers, a shield module below the libOS in the enclave and untrusted runtime outside the enclave. This implements a shielded version and enclave by calling out the untrusted host. The code inside the enclave is trusted computing based. It implements the drawbridge API required by libOS to limit the subset core of operating system operations. The shield module is in charge of protecting the libOS and application from outside attacks to enclave. It does this by carefully validation of all parameters and result paths across a narrow interface with untrusted runtime. This untrusted interface accesses the boundary that must allow the shield to verify the correctness of all operations. The interface prevents operating that give any implementation freedom to the host operating system beside physical resource allocation. This interface makes verification efficient and also limit the scope of attack. Haven implements only 22 of the original 40 down call from the drawbridge. It allows call to commit free and protect specific page, thread management, and singling input-output stream to access untrusted storage and network, and a source of a system-time untrusted runtime that run within the untrusted interface access, the primitive bootstrap, and is trusted by neither the enclave or the host kernel. It deals with creating the enclave, loading the shield, and forwarding calls between the enclave and host operating system.
Hello everyone, my name is Rich Sparks and I will be doing part 2 of the analysis. So what is the problem addressed in this paper? Well, simply trust. We need to ask ourselves, do we need security in the cloud? And The answer to that is yes, we need to protect ourselves from malware and other types of attacks. How do we protect our existing and legacy applications? Before we answer those questions, we need to have a solid understanding of what the goal in security is, and that is the CIA triad, which stands for confidentiality, which is the secrecy of our code, integrity, which is making sure our code and our data is unchanged, and availability, which is making sure that everything works properly and is accessible. The next question we want to ask is this an important problem? Yes, because hardware security models are not always enough. Law enforcement bodies can interfere with the user's security. And also, the cloud provider is limited to offering just raw resources, such as processor cycles, storage, and networking. It does not provide shielded execution, meaning that an attacker could find ways for a cloud provider or application to expose its secret keys. The authors of this study have developed a system called Haven, and it solves this because it is essentially shielded execution. Did the authors convincingly motivate that this is a problem? Yes, they introduced the notion of shielded execution, which means that it will protect the confidentiality and integrity of a program and protect its data from the platform it runs on, such as the cloud, virtual machine, or firmware. The author's goal or objective is to facilitate existing server applications in the cloud with a level of trust and security that is similar to a user operating their own hardware and protected security. So is this an important problem? Yes, malware can be in and out of the cloud. Hardware attacks such as side channel attacks and Yago attacks are serious threats. Yago attacks are where a malicious OS subverts a protected application by exploiting the application's reliance on the correct results of system calls. An example of a side channel attack would be where somebody takes out the memory modules in a computer, freezes the secret keys, and then uses various methods to extract them. So with that in mind, would the average user trust cloud services if they knew all these vulnerabilities? So was this study theoretical, practical, or both? Both, because we believe the authors state that they have never tested the Haven system on actual SGX hardware, but rather have tested it on Intel's emulator. This is more of an application approach, but in theory builds the foundation for further security designs in the cloud. It is also quite practical because every application needs to be secure from malware, viruses, ransomware, spyware, hardware attacks, etc. Were there any solutions out there for this problem? Yes. As mentioned before, secrets were typically dealt with by hardware security models. These are devices that protect secret keys and also do cryptographic functions. Alongside Intel's XGS, there is also ARM's Trust Zone, which is very similar. However, this research article focuses on SGX with the Windows 8 platform. Also, physical security provides locks and detonations of keys or data if the devices were tampered with. What's wrong with these solutions? Or why aren't they sufficient? The problem with these solutions is that they do not guarantee safety and security from the cloud and any other malicious attack. Now, we want to step back and ask ourselves, what is the novel contribution and solution proposed in this paper? Starting with number 1, trust can be exclusive from the cloud. Number 2, protection for legacy applications. Number 3, SGX being pushed beyond its intended design. And number 4, the Haven prototype, which achieves secure and private execution of unmodified applications by leveraging the hardware protection of the Intel SGX. This also contains a region of address space known as the enclave. Is this a significant contribution? Quite significant, since the authors are raising the bar of security with the conventional models used and expanding on it in regards to the emerging cloud computing infrastructure. Also, Intel's SGX was never designed to secure an entire application, but rather a portion of an application's code. The authors were also able to go beyond that and push SGX beyond its normal parameters. So was this study original, trailblazing, or incremental? Original in that it's thinking outside the cloud for security. Trailblazing in that it covers Yago and side channel attacks. And incremental because it is expanding the work of hardware design by Intel on a software level. We would say all three, but more incremental and original than anything else. This is due to the fact that the authors are expanding what is already engineered in the CPU and expanding the pool of security. What are the similarities and differences between this work and existing solutions? Existing solutions have been hardware state modules. They are dedicated appliances that rely on tamper-proof mechanisms to protect critical secrets. Similarly, they share the same end result, protection. The difference is how they do this, how effective they are, and how efficiently they solve the measure of security along with potential trade-offs they entail. Is the related work discussed enough? Not so much due to the fact that earlier work does not solve all the current and evolving problems of the cloud. In terms of SGX, there has been a number of updates and revisions. The authors do note that this is an ongoing process, and we could expect to see many of the issues addressed in their paper, such as asynchronous exits out of the enclave, to be resolved in the future. So we want to look at what was the theoretical analysis, the prototype implementation, and the simulations when necessary. Well, the researchers used a virtual machine of SGX. SGX supports CPU-based attestation, which is the enabling of a remote system to verify cryptographically that a specific hardware has been loaded in the enclave, and also the enclave itself, which consists of the Windows 8 drawbridge, which is a sandbox, in conjunction with the libOS and the Pico processes of Windows. So how did the authors demonstrate that their solution works? Well, they used existing hardware technology, which is the Intel SGX, and they designed the Haven system around it. And the Haven system is used to write code in and out of the enclave, as well as page mapping in a virtual address space. To prevent against unwanted system calls and Yago attacks, the library uses the libOS to guard against this. The Haven implementation ran with two common web applications, SQL Server and Apache. In this section, we're just going to do a quick design overview of SGX and its components. To the left, we have the diagram of the virtual address space and the physical memory that is managed by the enclave and the thread control structure. There is also, you have this EPC here that stands for the enclave page cache. This just verifies that the page tables have been properly checked. To the right, we have the diagram of the basically the whole Haven components and its interfaces. And it starts with the Pico process, which is managed by Windows. Inside we have the enclave, and inside the enclave we have the application that runs the unmodified binaries. In the library OS, this is where we get into the subset of the Windows API, and the library OS makes sure that the OS is not prone to Yago attacks. This also works with the drawbridge API, and this drawbridge API ensures that the kernel is functioning correctly. There's isn't any types of scheduling or file system issues. It's also making sure that the untrusted interface with the host is working well. So it's a pretty secure system that, again, takes not just small pieces of code, but with the Haven design, takes in the entire application's code and protects it from an untrusted source. In this next slide, again, we want to ask ourselves, did the authors demonstrate that their solution works? And if so, how many times were they able to run their experiment? Well, after reading the paper, the authors did not specify how many times they tested their application. We know that it was implemented on a virtual machine and not the actual hardware, but we can assume that they ran it enough times to aggregate enough data to achieve a level of throughput, and also learn the general performance of the two applications they ran, that being the SQL and the Apache web server. Did the authors achieve what they set out to do? Yes, they achieved 2/3 of the CIA triad, which are confidentiality and integrity, in their Haven system. The authors did not mention whether availability was achieved, but we can assume that this was due to potential compatibility issues. Despite the slowdown of performance in the applications they ran, the authors were able to achieve security outside the cloud, which was the goal of the study. In this next slide, I would like to go over the results. I'm not going to spend too much time on this, but basically, in their server and Apache application, Haven tend to slow down the performance of these applications. And you can see that wherever there is Haven or enclave processes, there is a decrease in performance across the graphs. With that in mind, security comes at a cost. So the next question we want to look at is whether this paper was well organized and presented. And the answer is yes, very much so. It starts by addressing and defining the problem, a background of current security problems and potential solutions are addressed. It then goes into the design challenges, implementation, and acknowledged limitations with hardware and OS software were also noted. It then briefly went over the performance, and then it was followed up with the results and its collaborations that made the study possible. So what did we learn from this paper? Well, not only is trust a significant issue with cloud computing, but being able to unlock the potential of new and cutting-edge hardware was also achieved. With that in mind, we should not only be protecting the data of our users, but we should also be ahead of potential challenges rather than being behind. In conclusion, we want to look at some pros and cons. Pros. With Haven, there is an enhanced level of trust. I would also like to mention that the authors noted that they lowered the DRAM frequencies to achieve an optimal level of throughput with their applications. However, I would not be surprised if this also allowed the SGX registers to handle more application code in the enclave than its recommended or intended use. Also, with Haven, you get a shielded execution of legacy applications. And lastly, Haven provides a model for security that is in and out of the cloud. Cons. The only problems that we saw in the study was the fact that the Haven's enclave was only designed for Intel and the Windows 8 platform. It does not mention whether other CPUs other than the ARM's Trust Zone have similar functions or capabilities. Also, it does not mention whether SGX is designed only for 32-bit or 64-bit CPUs. Since Haven is designed to work with legacy applications, we can only assume that the architecture is not an issue. Also, the software is tested on a hardware emulator. It does not guarantee actual performance. Also, how well does SGX handle dynamic allocation of code? Another thing, SGX has limitations with regards to the operating system, its system calls, exception handling, etc. And lastly, added security comes at a cost, such as performance. So I would like to conclude with a note from the authors. Why trust the cloud when you don't have to?